Okay, so I'm going to try to work some problems with cross sections that I really don't have answers for, so just bear with me. Okay, so this was example number 2. We already found internal forces at C, going from left and coming from right. Then we found shear moment diagrams based on equation, and now we're just going to take that same cross section and go to the next step, which is finding the normal stress due to bending. And if you don't know what's coming, when we start chapter 7, which is transverse shear in a beam, we're going to be coming back and visiting our shear diagram right there. So let's start with, it kind of looks like it might be some sort of an I-beam. And for simplicity right now, we are going to assume that it is symmetric because that just kind of helps us know that Y-bar is halfway down or halfway up, however you want to look at it. So remember, number 1, when I'm dealing with bending moments and finding stresses, is I need to look at my cross section and find Y-bar. I guess really number 1 is drawing a moment diagram. Okay, really if we want to go back and say, this is super important, because what happens is on exams and homework is you get a beam, and I say, what's the normal stress, the maximum stress due to bending, and I'll have students comment, you didn't tell me what the moment was. If you have a beam with loads, you can find a shear moment diagram. This is statics. That's why you took statics before you came into strengths. So I found Y-bar because I made it symmetric. So it's 7 inches from the top or 7 inches up from the bottom. Number 2, I need to find my moment of inertia. And when we have a complex system like this, that's made with more than just one rectangle, then we have to find the moment of inertia where we have to add that AD squared term. Because it's symmetric, I'm going to count these two areas as 1, because whether I come to the bottom or come to the top to the centroid, my area is the same and that distance is the same. So I'm going to start at the top. We're going to work our way down. So I actually have 2, and I have a rectangle, and our moment of inertia for a rectangle, remember, is BH cubed over 12. So I have a base of 10, a height of 1 cubed over 12, so that's a very small number, but we get the advantage by having it spaced at, this is 6, and then I have to go up another ½ inch to get to that centroid. So 6½ inches squared. This is where the advantage comes. By itself, very low moment of inertia. When we apply it to a system and put that area far, far away from the centroid, we get this term, which really builds up the capacity of our section. Because it's symmetric, that's why I went ahead and multiplied it by 2, because whether I go up or go down, positive or negative, we're squaring it. It's 6½ squared. Plus, we've done the top and the bottom. Let's do this one. Our base is, we're going to call it a 1. Our height is 12 cubed over 12 plus area 1 times 12. But this time our distance is 0. Okay, our distance is 0 because the centroid of this rectangle lies on the centroid of my system. So we are not getting that AD squared advantage, but we have the height. That's where we're getting the stiffness this way. It's why in a joist system, you put in your joist this way, because you get this BH cubed over 12, versus if you laid it flat by itself, it would be very boingy. Okay, very, very boingy. So we now have an equation for I. So let's get this worked through. We have 2, enter, 10, enter. I'm going to clear everything. 2, enter, 10, enter, 12 divided by, and then we have 10 times 1, and then we have 6.5 squared multiplied by 10, added to 0.833, very tiny, times 2, and now we're going to move down here. So we have 12 enter to the cubed power divided by 12, so 144, quite a bit larger than that decimal we had here, plus 0. So now when I add this up, I get 990.67 inches to the 4th. And for ease, I'm just going to call it 990. Okay, so I'm not going to be writing everything out. So now if I want to, oh, I forgot. The first thing I'm going to do, much like finding the centroid, is I'm just going to do a guess. What do I think the shape is going to look like when I look at the normal stress due to bending? Okay, I'm going to recognize we are working with a maximum moment here. It is positive. So that tells me it's a positive. So I have compression top, tension bottom. So as I'm going towards the top, these fibers are going to get shorter and shorter. So they're going to be in our compression zone. I know that I'm 0 at the bottom. And even though we have a width change here, it doesn't affect our normal stress due to bending, because what affects it is y, the height to the top and the height to the bottom. The height to where the web and the flange meet is the same, so they're going to have the same stress. So I'm going to just kind of guess that it's linear, like this, where I have compression and where I have tension. And I also know that the stress tension is going to equal the stress compression because it's symmetric to the top and to the bottom. I'm going to wait for that to catch up. I don't know why it's just very slow. I think it's because I'm so fast. Okay, that's my guess. So now what we're going to do is go back and find values. Okay, again, we need to find 2, except in this case, I know that my stress compression has to equal my stress tension because of the symmetry to the top and to the bottom. Our stress is MC for the maximum over I. And I have, I don't remember what that value was. It looks like it was 26-ish. I think it was like 26 point something, but we're just going to call it 26. So I have 26 kip feet, okay? I can't use that unit. I need to call that 12 inches per foot. Pay attention to units. C. C is from the centroid to the outermost fiber. Outermost fiber. 6 plus 1 is 7. 7 inches. And then I have a moment of inertia of 990 inches to the fourth. So whether I'm looking at compression or tension, they have the same magnitude. So I'm just going to take this, I'm going to do my 1 over button because I'm dividing. So instead of re-putting it in, I just did that. And then I'm going to say 26 times 12 times. Did I do that right? Let me go back and look at my arguments. Divided by. Oops, wrong way. Let's go back and look at arguments. We need to multiply. Swap, drop, drop. Okay, so that is 26 times the reciprocal of 990 times 12 times 7, and I get a stress of 2.2 KSI, kips inches, KSI, okay? And I know whether I'm looking at my compression of 2.2 KSI up here or my tension of 2.2 KSI down here, they are the same. So 2.2, 2.2. I'm already telling you this is tension on to the right, compression, whoops, that should be a negative, not a up and down to the left, and my units are KSI. So much like a shear moment diagram, you need to let us know what you're calling tension and what you're calling compression and what your units are, and then you can just label with numbers and you don't have to keep writing everything. Okay, so now let's look at this example, but this time let's switch it up. Let's have a new cross section here of 12 to 1, and let's continue this being 12, but down here, let's make it 8 to 1. This time, okay, I've got my moment diagram. I know it's positive, smiley face curvature. This time, I don't know where Y bar is because I have more area above than below. So I know that that Y bar is shifted up, okay? So I have to calculate, number 1, where is Y bar? Where is Y bar, okay? So Y bar equals the sum of my areas times Y tilde, which is the distance from my global axis, okay? And we're trying to find X prime. So our global axis to each of my 3 segments. I'm going to start at the top since I'm measuring from the top. You could also draw this at the bottom and measure up. Your Y bar will be a different value, but we will end up with the same. Your Y bar plus my Y bar will equal 14, okay? So let's start with the top. My area is base times height, and it's 1/2 inch down, plus base times height, and we are at 1 plus 6 is 7 inches down, plus base times height, and this time we are down 1 plus 12 is 13, And then half of that gives me 13.5 inches. Okay, and now I can just go base times height plus base times height plus base times height. And here I get a y bar of, bear with me, 12, enter 1 time, 0.5 times, 12, enter 7 times, 8, enter 13.5 times, plus, plus, 12, enter 12, enter 8, enter, plus, plus, divided by. I get 6.2 inches down from that very top global. So now I know where my y bar is, 6.2 inches down. Conversely, if you worked this from the bottom, if you need extra practice, you have 14 inches tall minus 6.2, we should be 7.8 inches up. So you guys can be working these problems and pausing the video and working problems and pausing the video so you can get practice and figure out if what you're doing is correct. So now as I'm looking at my cross section, okay, here's my cross section. I hope you understand now it's a linear distribution, okay? And I know I'm going to be in tension in the bottom and compression on the top, but do I have the same values this time for my compressive stress and my tensile stress? What do you guys think? Do you think I have the same value? Okay, we don't, because we have a different value of C to the top. That's only 6.2 inches, while to the bottom, it's now 7.8. So if we want to find compression to the top, or stress at the top, I have a moment of 26 kip feet times 12 inches per foot times going to the top is 6.2 inches over, oh, shoot. You know what we didn't do is find our moment of inertia. Sorry about that, guys, and I'm going to run out of video time. Let's find our moment of inertia. Equals, luckily we have all rectangles. We're going to start at the top. BH cubed over 12 plus BH, and then we are going from y bar, okay, we know this distance, 6.2, minus a half an inch squared, because that gives us the distance in between, okay, plus base times height plus base times height. This time, again, we are going to take our y bar, 6.2 inches, minus, okay, because I know if I come down this way and then I go here and I get this distance, which I already have, 7, then I will be left with the distance in between, okay, plus base times height over 12 plus base times height times 6.2 minus, okay, this time I've got this, I'm going to minus, I need this distance, which we already have up here, 1, 12, 13.5. How did I go from 12, 13, okay, that's right, 13.5 squared. And if I notice, if I take the 6.2 and then I subtract from it this distance, I end up with, again, the distance in between. It helps to have a system because then your brain can just go on autopilot and we would get a value for our moment of inertia. Now my video is fixing to run out. YouTube is not letting me post anything hardly above 15 minutes. So you guys can work through these numbers and then you can go ahead and find the compression and tension. And you might as well find what's happening at our web flange interface. And what you're going to find is we're not looking at the width, we are just looking at the height, and those C's are the same, just like these C's are the same, okay? You plug all those in, you will find a linear relationship. I would say try to draw things somewhat to scale because it makes it easier to understand. But I hope you see here that our tensile is greater than our compression because of the C value, but at the end of the day, we hope that they are both below yield. Okay, I'll be working another problem soon.